All right, number 5, we want to find the cardinal number of each of the following sets. So cardinal number is just how many elements. And normally you'll see this little symbol N next to a letter representing a set. Okay, this is what we mean cardinal number. This is the symbolic form. And it just means count them. How many elements do you have? So there's a couple methods we can use. We can use the methods we learned in the previous section when we were using sequences, finding the sum of them. But let's just take A for example. I'm looking at this pattern. We have 215, 216, 217, and I'm just going to go dot dot dot, and we have 21114. So I noticed that this pattern is already counting by ones, but it doesn't start at the number 1, it starts at 215. So all we really need to do is shift. I'm going to be manipulating these formulas if I can. So I'm going to shift this back so that it starts at 1, and that will allow me to count how many terms. So what I mean, since we started 215, if I wanted to start at 1, I would need to subtract 214. That would give me 1. And you would imagine doing that from every term. Basically, this is the most important one that we're concerned with, because that's the last one, 214. So if I were to subtract 214 from every term, this would be 1, this would be 2, this would be 3. So it'd be counting by ones. And then up here, if I subtract 214, we would have 900. So this pattern has 900 terms. Now you can also use the method that we learned in section 2.1 with the sequence. You have AN, your last term, is equal to your first term plus the difference times n minus 1, and use that formula to solve it. However, with a little manipulation you can kind of get there pretty quick as well. So 900 is going to be the number of terms, the cardinal number of terms in this first sequence. Okay, so B, same thing, cardinal number. So again, we can use this formula. However, I like to manipulate them if I can with a little work. So this pattern starts 3, 5, 7, and then continues, okay, up to 101. All right, so what I want, this is counting by twos, adding 2 every time. Okay, so I want to divide it by 2. Since it's counting by 2, I want to divide that. And right now they're not equal. They're not even, so I can't divide by 2. So I'm going to manipulate this. Instead of shifting it, I can either add 1 or subtract 1. Either one would work. I think it would be better if I subtract 1. The reason why, because I'll have 2 here, and if I divide by 2, then I'll be at 1. So I'm going to subtract 1. Imagine subtracting 1 from every term, and then this new pattern would be 2, 4, 6, so on up to 100. That's the last term. And then, since they're counting by twos and I need them to count by 1 so I can count how many terms, now we're going to divide everything by 2. So that's what you need to think about, but it's mainly the last term. If you divide everything by 2, you'll get another formula, which is 1, 2, 3, dot, 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 up to 100 divided by 2 is 50. Okay, so there's no particular set of rules I'm following. You're just kind of using some math intuition to manipulate these sequences and count. But again, this formula right here will always work if we're adding the same difference. Just use your last and first, and we've done that a few times. So this is 50 terms in this one. Now the third one This one is increasing pretty fast. It doesn't look like there's a pattern, but there is. So we start out with 7, and then 14, and then 28, and then 56. And it's just getting really, really big. Goes all the way up to 1792. Okay. So at first it looked like we were adding 7, but then when you get here, adding 7 would give us 21. So that's not the same. So it's not adding. Is it multiplying the same number? If I divide, take 14 divided by 7, we get 2. So it's like a difference of times 2. And if I times 2 here, 14 times 2, we get 28. So it is multiplying by 2 every time. This is a geometric series. So remember that geometric formula, AN, and I think it's probably going to be best to do this one with the formula. AN is equal to A1, the first term, times that difference that you're multiplying by, which is 2 raised to the n minus 1 power. Okay, so this is the formula we're going to use. I am going to input the 1792 equals the first term 7 times the 2 to the n minus 1 power. Alright, to solve this, we're going to divide off the 7. Okay. And so when I do 1792 divided by 7, let's see what we get there. So I'm going to do 1792 divided by 7. That gives us 256. 256 is equal to 2 to the n minus 1 power. Alright, so now we need to figure out what is 2, or 2 to what power is 256. Okay. So a couple ways we can do it. We can look up a power table. I'm going to use a calculator. I'm going to go to y equal, type in 2 raised to x. So x is just going to be a variable. It's going to put in 1, 2, 3, 4, 5, and just give me a bunch of different numbers. Okay, so second graph to see the table. All right, so if I plug in a 0, I would get 1. If I plug in a 1, I get 2. So I'm looking for which number over here is giving me 256 right here. See how 8 is 256? So let's verify. So if I say 2 and I raise it to the 8th power, we get 256. Okay, so this formula down here, I'm kind of moving over, running out of room. I'm going to say 2 to the 8th is equal to 2 to the n minus 1. Now that we have both these the same, we can ignore them and just focus on the top. This is a different part. So 8 equals n minus 1, and if we add 1, we get that 9 is equal to n. So this is why I try to manipulate them. The formula will get you there. It just takes a little bit of work and a thought process, and if you can manipulate them, you'll be all the better for it. Okay, so n is 9 in this case. Okay, and then we want to know the cardinal number of this set. So it is the set of all x's such that x equals k cubed, and they're saying k is going to be the numbers 1, 2, 3 up to 56. So these are the numbers we're using. These aren't the sets, but these are the numbers we're using, and we have 56 elements. We can see because we start at 1 and we stop at 56.